In this video, I answer my students' questions. Specifically, we're going to look at questions that involve the simultaneous linear and quadratic solutions, as well as how you can graph quadratics. From there, we move on to the curriculum content, which covers how to use the bisection method. Enjoy. Okay. Just fix my windows up a little bit so I can see what's going on. Okay. At what coordinates does the graph of y equals -3? So quadratic equal linear. What coordinates? Okay. Image.
That's what we did just today. The first question, find the equation of the quadratic. Just the coordinates, but I don't get it because if you went through it fast, yeah, we had no time to do it.
So you're giving me two images there. Are any of those the quadratic and linear that you're talking about?
The first image is from 3K Unit 1 and 2, and then the second one that I uploaded from the textbook is I think it's the simultaneous linear and quadratic equation.
Yeah, so the one you put in the actual question box, you had, well, I guess we'll just do it, it's fine. Okay, easy enough to see the document camera?
Yeah.
Okay, that's good. So it was y equals -3x squared plus 5x plus 6, and we are looking for where it intersects the second line, which is y equals 4x plus 5. Have I got that right?
Yep.
Okay. So when you want to find the intersection point between any two lines, what do you typically do?
You find the. Well, what's the question? Sorry again.
So if I wanted to tell you to find the intersection points between any two lines, let's just create some random whatevers here, a line here, a line here. This is some y equals mx plus c. This is some other y equals mx plus c. How do I find that spot?
By subbing those two coordinates.
Yeah, subbing them into each other. Same thing applies to linear and quadratics.
So you make them equal to each other?
Make them equal to each other, yep. So we're going to have 4x plus 5 is equal to -3x squared plus 5x plus 6. Cool. Mm-hmm. All you do is just solve this for x. So what would you do in this case to solve for x?
So you just move 4x plus 5 to the other side and then equals to 0?
Yep. 0 equals -3x squared. 5x and 4x becomes x, and that becomes 1. Okay?
Mm-hmm.
And then, yeah, you just solve this as you would for any other quadratic. Probably a quadratic formula type question.
Mm-hmm. How do you sketch that on a graph?
How to sketch? Mm-hmm. You wouldn't want to sketch this because this isn't necessarily a graph that you have. This is just what happens when you equate these two things together.
Mm-hmm.
Like this is a graph, this is a graph. You could sketch this if you wanted to, but it's not like it's one of the original things that you have.
Oh, okay.
What you'd probably be expected to do instead would be to sketch this, and then you would draw a little dot of what that intersection of.
So we got to sketch those two separately and then.
Well, you just told me what's the x coordinates, which means you don't need to sketch anything. But if your question says sketch, then it's probably talking about these two sketched
on the same graph, and then state where the coordinates intersect each other, right?
Well, I mean, your question as written was just what are the coordinates, in which case you don't need to sketch anything. But if it does tell you to sketch, then these are the things it's talking about.
Oh, okay.
Do you want me to go any more detail as to how you solve x in this one, or is that clear enough where you would go from
there? If you could.
Yeah, sure. So I guess first things first, you could test to see if there even are solutions to this, in which case you do discriminant. But this one does imply that there are coordinates, so you wouldn't really bother doing that extra step.
Okay.
So you just need to know this is your A, 1 is your B, and 1 is also your C. And so I would just go straight to quadratic formula here. X equals -b, which is 1, plus minus square root of b squared, again just 1, minus 4 times A times C. all over 2a. Continue to simplify this. X equals -1 over -6 plus minus square root of 1 minus, well, plus I guess,
13
to 12, so 13, yeah. X equals 1 over 6 plus minus root 13 over 6. So those will be the x coordinates that you give. In fact, you could probably just give that as an answer because it doesn't even say what the y's are. It just says what are the x's.
Do you think they would ask that that equation to just sketch on the graph and the test or no? Because that's 1 over 6 plus minus root 13 over 6 wouldn't really be a number that you could sketch on the graph.
Yeah, for sure. So if they said sketch the graphs and then label the coordinates, what you would do is, well, firstly sketch the quadratic, which, let's see, well, maybe the linear is easier to start with. You're going to have the 5 like that. 1 over 6 plus minus this, probably going to be plus minus either side like that. So your quadratic is probably going to do something like this, if I were to guess. And then these spots here, you would label with, well, the x coordinate, this one would be 1 over 6 plus root 13 over 6, and then whatever the y value is at that spot, which would be maybe not the worst, because you just put this into the linear, make it a bit easier. And you'll do the exact same thing for this spot over here. That's if you're required to do that, which you aren't by this question.
All right.
Cool.
Yep.
Okay, so that's that one. I've got a couple of images here. Let's say find the equation of the quadratic that passes through 3 points. Okay, so this is a typical question which are called families of functions, style questions.
Yeah.
So now I can actually get up some additional notes we can have a look at. And I can show you the procedure by which we handle all of these, really. Okay, so this will be under quadratics, applications. Okay, so I have an additional screen share. Can you see that one?
Yeah.
Okay, that's good. So whenever you're doing families of functions things with quadratics, or I guess with any function, quadratics in particular have 3 ways in which you can represent them. You can either do the polynomial form or the just expanded quadratic form.
Yeah.
And you have the 2 factorized forms. One is for x-intercepts and the other is for turning points. Typically, you want to avoid using this top one wherever possible, but your question, unfortunately, is the one where you would have to use that top form. So you know when to use what based on what information you're given. You're given 3 random points, and so you have to do a 3-way simultaneous to solve that.
Oh, simultaneous?
Simultaneous, yeah. So very briefly, the others, like if you had x-intercepts, for example, you could use this form and immediately figure out what those coordinates would be. If you had a turning point, you could stuff it into the turning point form instead. But because you have, what are the coordinates exactly? You've got, cut that off, you've got -2, -1, you've got 1, 2, and 3, -16. They didn't even give you the y-intercept. How sad.
Yeah.
So this is a true 3-way simultaneous that you would have to do with a generic y equals ax squared plus bx plus c. You want to know where your a, b, and c are from that.
So the whole point of those 3 coordinates is to turn it into a quadratic ax plus bx plus c, right?
Yeah, correct.
Oh, okay.
So the question reads, find the equation of the quadratic. So this is some generic quadratic, and it has to pass through those 3 points. And you can guarantee that by ensuring that you sub in all 3 points into this quadratic. So simultaneous, basically. Want to see what that looks like, or are you clear enough how you would do that?
Yeah.
That was yes to both questions. Which one? Do you want me to just do it?
For the first one, yeah.
Okay, cool. So you may need more space on the paper, but I guess we'll figure that out as we go. So y equals -1, a negative 2 squared plus b, negative 2 plus c. Okay, negative 1 equals 4a minus 2b plus c. We can call that equation number 1. Then from there, we'll sub in the other point. So we're going to have 2 equals, that's just a plus b plus c, because x equals 1, nice and easy. And then equation number 3 is going to be y equals negative 16. 3 3s are 9, to 9, then an a, plus 3b, and then again plus c. Equation number 3. When you have equations like this, when you have more than 2 simultaneous, it's typically easiest to go with a simultaneous, an elimination approach, because you have the opportunity perhaps to cancel out more than a single variable. Looking at this one here, I'm not really seeing the opportunity though, unfortunately. Sometimes you can like multiply one thing and you can kill 2 things at once.
Yeah.
In this case, I'm not really seeing. Well, let's think. Can we find one? Nah. Okay. So we'll just do some basic elimination method. So it doesn't matter which way you go, just cancel out one variable. Pick one of them.
Okay.
Which one would you pick? Just out of curiosity, I'm curious.
First one wouldn't be easier.
So you do need to pick 2 equations, but I'm asking like which variable, A, B, or C, would you be aiming at cancelling?
A.
A, okay. So to achieve a cancellation of A, you would have to multiply an equation to get it up to a spot where you can cancel it, and then you could do elimination method. A slightly faster approach would be to try and cancel C, because you can directly do a subtraction immediately.
Right.
What you're doing is fine though. You could multiply this thing by 4, for example, and then cancel. But it's just ever so slightly more tactical, I guess you could say, to cancel out a C. And it doesn't matter particularly which way you do it. You could do equation 1 minus equation 2, 1 minus 3, 2 minus 3, all of them get the job done. So let's try that. So equation 1 minus equation 2. So equation 1 was this, equation 2 was that. 1 minus 2, so we're doing top minus bottom always.
Yeah.
Negative 1 minus 2 is going to give us negative 3.
3.
Then we got a 4a minus a for a 3a. We got a minus 2b minus a b for a minus 3b. And as designed, the c's will cancel out. So one thing you could do from here is just divide everything by 3 again. So negative 1 equals a minus b. And just to give it a name, we could call this equation 4. So the goal behind doing a 3-way simultaneous is to create 2 new equations that just have 2 of the same unknowns. So in this case, we have an a and a b in this equation only. So we've already done a 1 minus 2. We have 2 options now. We could use 1 and 3, or we could use 2 and 3. Doesn't actually matter which way we do it, as long as we cancel the same variable, c. So the next easiest one to me sounds like, well, they're all a bit shit. Maybe we could just do 1 minus 3. But again, it doesn't really matter. 1 minus 3. So again, negative 1 minus negative 16 is going to be positive 15. 4a minus 9a, that's going to be minus 5a. Minus 2b minus 3b for minus 5b. And then, of course, the c's cancel out once again. This one actually turned out to be quite nice, because once again, we get a divide by 5 that can help us out. And so what you're seeing now is that we have 2 equations with 2 of the same unknowns. You just do simultaneous again with just these ones now. So again, you could do elimination method by adding the 2 equations together, or you could do substitution. It's personal preference really at this point. Do you want to see it go further, or happy enough to see where you are?
Yeah, it's alright.
It's alright to stop here?
Yeah.
Okay. So that's that. You get all your a, b, c, and then you just plug that into ax squared plus bx plus c. Okay, next up, solve each pairs of simultaneous equations. That is the same question that we just did up here, which was finding intersection points. So you had a quadratic and a linear. When you solve those, to solve those, you would equate those two things together and grab your x, sub that back in to get a y. So it's the same approach as the first question.
So, yeah, it doesn't matter if it's 2 coordinates or 3, right?
2 coordinates or 3. Well, this will only ever have a maximum of 2 coordinates because it's a linear and a quadratic. It could have anywhere between 1, 2, or no solutions, depending on how it's how it looks.
Discriminant?
Yeah, discriminant, basically. Yeah, how many times does it intersect? Let's see, do I have a picture that I can share with that? I think I can. Simultaneous linear and quadratic. Yes, I do. So here's the possibilities. You could be tangent, if you're looking at the other screen share with the notes. It would be
So
like,
if it's tangent, there's only one solution to it, right?
yeah, one solution. That'd be tangent. 2 solutions would look like this. You're cutting at 2 spots. No solutions, they just don't
would
touch.
be just parallel, right? Yeah. Well, not really.
Well, no solutions just means they don't touch. And you can use discriminant to solve number of solutions ahead of time. It is a bit more complicated than what you might think at first, because you don't find discriminant of this quadratic. You find discriminant after you equate the linear to the quadratic, because you want to find the solutions that this thing has. So this is your a term, this whole thing is your b term, since it's the coefficient of the x, and this whole thing is your c term. You do discriminant on that to find number of solutions between the two equations. So that's another layer of complexity when it comes to quadratic linear stuff.
Also for that,
go ahead.
For the ax squared plus, brackets b minus nx plus c minus d in brackets equals 0, how do you do the discriminant for that?
Yeah, so it's just this. So this is your a term, this is your b term, this is your c term. Yeah, b squared minus 4ac is what you're seeing down here.
Oh, yeah.
Yeah, so it's the same equation, just the b looks different and the c looks different.
Oh, okay.
I have examples if you want to have a look at that. Yeah, okay. So if you wanted to know ahead of time how many solutions this pair of equations has, you would start by still equating those two things together, which in this case means quadratic on one side, linear on the other. In this case, everything cancels down to just x squared equals 0. So it's pretty obvious to see that the only solution here is going to be x equals 0. But just to be devil's advocate, using the discriminant method, you do discriminant of this thing, where a equals 1, b equals 0, c equals 0. Sub it into discriminant. Discriminant equals 0.
Okay. So whenever b or c is not given, it just equals to 0, right?
Correct. Yeah, precisely. That's one possibility. If you have 2 solutions, for example, again, it all starts the same. Equate them, simplify, discriminant of this thing. This discriminant is positive, so you would expect 2 solutions for this. And then lastly, no solutions. Again, same thing. Equate, simplify. Discriminant of this becomes negative. No solutions.
That means no solution.
Yeah. Shall I go in any more detail into that?
No, not really.
Okay, that's good. So those are that's that screenshot you gave me. The other one you screenshotted 4 and 5 from the Cambridge book.
Simultaneous.
Was that again? Sorry.
That was simultaneous, right?
It was. Yeah, hang on. It was quadratic formula to find x-intercepts, axis symmetry. It sounds like it's just sketching graphs of parabolas.
You know how we get to the part that we do sketching the graph, right?
Yeah.
For example, we get to x equals plus or minus or now let's say x equals 2 plus or minus square root of let's say 17.
Yep.
Over like 2. How do we actually turn that number into decimal, or like you could understand that number so you can sketch the graph easily?
Okay, so that's two things. One is you don't turn it into a decimal, at least not one that is anywhere near accurate. But the other is, yes, you can still get an idea of the only thing you care about is if it's positive or negative, more or less.
Yeah.
And or because it's easier to know which one's bigger than the other, because when you add a number, it's always going to be bigger than if you subtract a number.
Yeah.
The only thing you really care about, as I said, was if it's negative or positive. So,
And then when you,
go ahead.
so when you're sketching, you just put in the whole thing, as in like x equals 2 minus root 17 over 2 on the actual graph, right?
Yeah, that's exactly what you would do. You give the exact always. If it says decimal, then you need a cas. Like it's just not going to be any other way.
Oh no, as in like in a test where you're not allowed to use calculators. So that was my question.
Yeah,
so
yeah, you would give the full exact. As for identifying whether that's a negative or a positive number, well, remind me what the numbers were again.
Well, it was 2 plus minus root 17 over 2. I don't know if it's correct or not, but it's came to my mind.
Yeah, no, that's fine. It's just numbers at the end of the day. Okay, so all divided by 2, like I've got here.
Yeah, all divided by 2.
Okay, so I would then just go one step a bit further and just do 2 divided by 2 is 1, and then plus minus root 17 on 2. So just by looking at this, I know this is the subtraction is going to make this negative, and the positive is going to make this positive. The reason why is because you can get an estimate of what root 17 would be like just by sort of testing whole numbers. So if you think about the square root of a number as just what two numbers multiply together to give 17 in this case, you can get an idea of where it might be. So if you were to test 3, you would get 9. 4 fours are 16. It can't be much bigger than 4.
Yeah.
And so let's just say it's between 4 and, I don't know, 4.2. Something like that. 4.2 is probably wildly too big. 4 is pretty close anyway. Let's pretend it's 4.
Okay.
If we subbed in 1 plus minus 4 over 2, and this is as small as it can possibly be, you're getting 1 plus minus 2, which gives you negative 1 and 3.
Oh.
So already, smallest possible estimate of 4. It's not correct, but it's, that's erring on the side of being worse. Still gives you a negative. So, if you make this any bigger, this just gets more negative, this just gets more positive. And you already know that 4 is too small anyway for a result. So by doing this sort of idea of just testing some integers and seeing what the relative magnitude of the root is, can allow you to figure out if it's positive or negative.
All right.
Clear enough on how you go about that?
Yeah.
Okay. That answers that. I am looking at a question you've got here about sketching parabolas. I believe. Where's that? So unit 1 and 2 is what, chapter 3, I think, for parabolas?
Yeah.
Yeah, graphing.
Unit.
It's probably after what, 3H, I'd guess. Do you know where it was? Just so I can get it on the screen share. That's okay.
I think it was. Well, hold on. I think I'm lost in. Oh, it's 3H. It is.
Yeah.
Question.
Found it.
I think question 4.
Okay. Well, there's a lot in question 4. I'm guessing the whole thing is a bit iffy for you.
Yeah.
Okay, that's fine. So it says sketching these parabolas. Specifically, it wants you to use quadratic formula to find the x-intercepts and axis of symmetry to find the turning point. Okay. So it's just using your understanding of quadratic formula and the axis of symmetry equation to get the key features of a parabola. When you sketch a parabola, what key features do you need to know?
Turning points, x-intercepts, y-intercept. I think that's all you need to know.
Exactly. As long as you have those things, you can sketch the shape of it, and you may have to rub out some bits if you have a domain applied. But that's fundamentally it. Quadratic formula. What does that tell you?
Use the quadratic formula to find the x-intercepts. So we got to factorize that.
Well, it says use quadratic formula, so you don't want to factorize it if you're using quadratic
Oh
formula.
yes, so we're using negative b plus minus b squared minus 4ac over 2a.
Yeah. So that basically the take-home message there is you can use quadratic formula to find x-intercepts of a quadratic if they exist. And the other thing is axis of symmetry. What key features that tell you?
Axis of symmetry. It's the midway of the two x-intercepts, right?
Yeah, precisely. And what does that correspond to as far as one of the three key features you mentioned?
Turning point?
Yeah, the x of the turning point. So this question just telling you to use particular method of getting those key features. So if we just start with like 4a, for example, you're going to have your y equals x squared plus 5x and then minus 1. And all we're doing is, well, we can start either way. Axis symmetry is pretty quick and easy to do. It's just x equals negative b over 2a, where our b is 5 and our a is 1. So already the x coordinate of our turning point is going to be negative 5 over 2.
Yep.
Okay. To get the y coordinate, you just sub that back in.
Doesn't it mention the y coordinate in the equation itself, negative 1? That would be c, right?
That would be your y-intercept. We're talking about the turning point, though.
Oh, okay.
Yeah, which probably isn't going to be the same thing. In fact, it won't be.
It won't be.
They're only the same if you have no like x term in there. But okay, negative 5 over 2 squared plus 5 times negative 5 over 2 minus 1. Just a bit of math here, nothing too crazy. Y equals 5 5s are 25, 2 2s are 4. Again, 5 5s are 25. This time it's over 2. Y equals, so we're going to have negative 25 on 4, because this becomes 50 over 4, minus 1. Y equals negative 29 over 4. Yeah, negative 29 over 4. So final coordinate for turning point is going to be negative 5 over 2, comma, negative 29 over 4. Okay, that's turning point. And now for the x-intercepts using quadratic formula. So again, a, b, and c. So x equals negative b, which is negative 5 plus minus square root of b squared minus 4ac all over 2a, where a again is 1. And then, yeah, just some more math. Negative 5 over 2 plus minus square root of 5 5 is 25 plus 4, so 29. X equals negative 5 plus minus root 29 over 2. This may or may not simplify down a bit more with surds, but it's just sort of whatever. You cool enough with how to simplify surds?
Yeah.
Yeah. So those become your x coordinates.
Yep.
So we have turning point, we have x. All we got to do is sketch now. So again, sketching, we know, well, we know it's a negative. No, it is a positive parabola actually. So it's going to start. Going to have our negative 5 over 2 for the x, negative 29 over 4 turning point, and then we sort of run into that issue before where we're trying to figure out, is this second coordinate a positive or a negative? Like, do I go here, here, or do I go here, here?
Yeah.
I'll let you take this one. Is the positive going to be, is the plus going to be a positive, or is the plus still going to be negative?
Wait, hold on, negative 5 times. That'd be still. Is it 24? Is that root 24?
Root 29.
29. That would be. Wait, hold on, let me just go 3 times. Do we have square factors of 29? Not really. That would be on the positive side.
Positive side? Okay. Why is that?
Yeah.
What was your
It's
estimate?
because, so let's say it's -5, negative root 29 over 2. So negative would be, you can't really divide it, right? 29, square root of,
Well, 5 fives are 25, right?
yeah, 5.
And 6 sixes are 36. So you know it's somewhere between 5 and 6.
So that would be -10 over 2, right?
Well, if it's 5,
Yeah,
you're doing the minus. So the minus will always be left. That's guaranteed. You want to know
yeah,
the plus version.
or the plus.
So at the absolute worst that you've got here, choosing a 5, what's the new x coordinate?
It could be, since 5 right? It
Mm-hmm.
would be closer to 0 point something.
Yeah. So even though, like, we know it's bigger than 5,
Yeah,
if you sub in 5, you get 0.
yeah.
Bigger number means more right, therefore
Mm-hmm.
has to be positive.
Yeah,
Cool?
yeah.
Okay. And so yeah, all we're doing is labeling now. So this is -5 plus the root,
Mm-hmm.
and this is -5 minus the root over there.
Yeah.
Draw, draw, and yeah. It's messy because I draw it small, but hopefully you draw it a bit bigger than I did.
Mm-hmm. So I've got another question
Mm-hmm.
relating to, stack or like test. It's more about, so it gives you, an actual, let's say, I had a question where it was, it's a picture of, a bridge, and it gives you, some thought about it, and you have to turn that information into an equation and then solve for that, right?
Mm-hmm.
So my question was, what's the best way to, turn that thing into a question and then solve for that?
Mm-hmm.
What's the extra steps that you could do or like practice before, doing the stack?
Yep. So whenever you have a depiction of some sort of quadratic, it's going to be
Yeah.
the families of functions things we talked about at the beginning. So if you look back to the screen share, you've got two possibilities. Three possibilities, sorry. If you have the turning point as part of your information, you would use the turning
Mm-hmm.
point form.
Okay.
So that would be like the peak of the bridge, basically.
Mm-hmm.
If you had the intercepts, so those would be like the support structures of the bridge. Let's even just draw a bridge so we can talk about the same thing.
Was that question was on the textbook actually. It was on 3K, I think.
Easy.
Families of
Okay.
three.
Let's have a look at it then.
It was question 11. I did solve that at school with my mate, but I then forgot about it again. It was question 11, 3K.
Yeah, okay. So you can see it's even labeled the families of
Yeah,
quadratics.
yeah.
So they talk about it again here. Here's your intercepts, here's your turning point, here's your four-way simultaneous.
Mm-hmm.
Remind me again which exact. It's this one, isn't it?
Question 11. Yeah, that bridge.
Okay. So here we have. So this is the important bit, knowing where your axis is.
Mm-hmm.
So this spot here is the origin.
Yeah.
So what we have is a point up here, because we're told this
Mm-hmm.
is 75 up, and since
Yeah.
it's on the y-axis, that's also x equals 0.
Yeah.
So one thing we can start to at least write down is getting that point. So we can say, if we know some function f of x is ax squared plus bx plus c, then we know at least f of 0 is going to be 75. Okay?
Yeah.
The other thing we know is that the next little peak of it occurs 180 meters later. So you got 180 and as the x, because this is x equals 0 at the beginning, and you've
Mm-hmm.
still got y equals 75 up the top here.
Yeah.
So what we're saying is that f of 180 is equal to 75 as well.
Oh, okay.
So that's two unique points so far. The next thing we're told in this is that the minimum height of the cable above the roadway is 30 meters.
Really.
That's talking about this spot where my cursor is. Can you see that?
So it wouldn't be touching that x-axis, right?
No, it's hovering above it.
Yeah.
So what we're told is that's the minimum height. So y equals 30 at this spot.
Mm-hmm.
What we can also do is figure out what the x is at that spot. Any ideas how?
No, not actually.
Well, take a look at the picture. You said it before, actually. Where's the turning point usually located?
And axis symmetry.
Yeah. So, what looks symmetrical here? What seems like a reasonable x to be symmetrical?
35? Wait, hold on. So, well, wouldn't it be 35 and
are you trying to do middle of this?
Yeah.
Well, that would be we know the y is 30 already. The y is the vertical.
Yeah.
We're looking for the horizontal. What seems like a reasonable horizontal to put there?
Assuming that it's able to 90 would be
You said
would
it?
it be 90?
90, yeah. Because it's midway between these two equidistant
Oh, yeah.
spots.
Yeah, since under 80 meters is all the thing axis symmetry, and then you got to divide under 80 by 2, which gives you 90, right?
Yeah, precisely. So, third point, f of 90 is equal to 30. This is 3 points. This is a three-way simultaneous, which we've seen how to do before. Actually a little bit easier than a three-way simultaneous, because this point f of 0 equals 75, well, if you sub in 0 into this spot and this spot, you just get c equals 75.
Yeah.
So
that would be able to y-intercept, right?
Yeah, y-intercept, correct. So it makes doing this one a lot easier because now you only, quote unquote, only have to do 75 is equal to, what is this, a bracket 180 squared plus b 180 and then plus c, which is the 75. And yeah, that's the 180 point. And then the 90 point is 30 equals a bracket 90 squared plus b 90 plus 75. That's if you have to do it tech-free. You shouldn't have to do it tech-free, but these aren't the worst numbers, even if they are big.
Yeah.
So this one, and yeah, it doesn't even become a three-way either because you've already got the c equals 75. Cool with that?
Yep.
Okay. That's that one then. Anything else you've come across?
No, I think that was it. That was all.
Brilliant. Okay. So we've still got some time in the group lesson remaining. The agenda today was to have a look at the bisection method, which is a method by which you can solve polynomials, which things like quadratics, without algebra. So sometimes you might have at this point been introduced to cubics.
Cubics, yeah, a little bit.
So what you'll find is that sometimes some cubics just cannot be solved with algebra. And what you can do is use these so-called numerical methods instead, which are typically things that you repeat over and over again to get closer and closer to a correct answer, but never quite the exact answer. This is what your CAS does a billion times in a second. It'll just do that over and over and over and over again until it gets... that's how it's able to approximate these roots. It's doing basically what we did, or we chose two integers, but it's doing it with decimals over and over again. So here's how that works. It might be a different algorithm, but we're going to look at one called the bisection method. So we follow these steps to do the bisection method.
Okay.
Won't worry about doing them right now. We'll look at an example first.
All right.
So suppose we have this cubic here. Looks something like this. You can get an idea of where this x-intercept is likely to be just by sort of subbing in some values initially. Like if you sub in x equals -2, you're going to get a negative number. If you subbed in x equals -1, you would get a positive. You know for a fact that because it's a transition, it must be somewhere between -2 and 1. Okay?
Yeah.
So that's what our first step is trying to do. We want to identify the interval, at least some initial interval from lower to upper bound, where the root occurs, where the root of a polynomial is just the solution to the function equaling 0. So again, as we said, that's going to be our -2 to -1. The next thing you want to do is figure out, when do I stop? because as I said earlier, you only ever get closer and closer to a real solution. You never actually equal the solution.
Yeah.
And so one thing you need to do is figure out when are we told to actually stop this process of doing it over and over again. There's three main types that you're likely to come across. One possibility is simply to end when your lower and upper bound have reached a certain distance between each other. So let's say I want to keep going until the gap between my lower and upper bound is less than or equal to 0.1. That's one possibility. The other possibility is we're looking at the specific y value itself. We're trying to get closer and closer to y equals 0. And so let's say we're going to call y anything between plus or minus 0.1. We're going to call as an okay y value. That's close enough to 0. That's one other possible exit condition. Lastly, you could just literally do it by the number of iterations that you're doing. So do 3 loops of the bisection method over and over again, and then stop on the third one, wherever it ends up. In this example, I'm going to use that first condition. So the gap between our lower and upper bound is going to be less than or equal to 0.1. Okay, so here's how the bisection method works. You take your interval, whatever it is, so in this case it's...
For the first step, -2 and -1?
Yeah, -2 to -1, yeah. And what you do is you find the midpoint of that. So if you look at this one here on the screen share, -2 to -1, the midpoint's going to be,
-1.5.
Precisely. Yeah. What you want to do is test the y value at that x value. In this case, it's negative. Whoops, that's bad. Highlight it properly, damn it. There we go. Because it's negative, we know for a fact that -1.5 is going to be our new lower bound. You take that -1.5, again, you find your midpoint. Did we get a negative or a positive? If it's positive, that becomes your new upper bound. And you just repeatedly shrink it by finding midpoints over and over again until you get closer and closer to the value. That's what's going to be explained here. So midpoint, -1.5, sub that x value back in and check. Did we get positive? Did we get negative? If negative, you have a lower bound. If positive, you have an upper bound.
So you got negative.
So now we shrink our boundary. Here's -1.5. Here's -1. Again, we want to find our new midpoint. All the while still checking our exit condition. So in this case, I've said we're going to exit. Is this the exit condition or is this just what it was? 0.5. Yeah, so we want to exit when it's less than or equal to 0.1. The gap between them is currently 0.5, and so we're going to keep going. Again, find the midpoint of these two spots. You've got -1.25. If you test the x value there, you're still going to get a negative. So again, we're going to shrink our interval. Now, it looks like this. Test the exit, we're 0.25. 0.25 is not 0.1, so we go again. Midpoint, test the value, it's positive this time. So midpoint would be here-ish, positive y. Again, interval is shrunk. Keep going, keep going, keep going, and eventually get to a point where our gap between them is less than 0.1, and so we're happy enough to conclude that our answer is the last midpoint that you got before reaching your exit condition. So we're happy to say that -1.18 is approximately where y equals 0.
Okay.
Cool?
Yeah.
That's
would
pretty much
this be something that we would be studying in year 11 or year 12?
Yeah. It is in the polynomials book right.
Oh, it is?
Right here. 6K.
Okay.
So this is page 253. Let's see. Yeah, page 253. Unfortunately, this book doesn't have any of the hyperlinks, so I've got to scroll directly to it. 53 bisection method. So it's talking about this exact thing here, where you can see you get closer and closer.
Oh, it is -1.5 and -2, that exact question.
Is it the exact one?
It's on the...
This one's a bit different.
Yes, start page of 6K bisection. Yeah.
That's a bit different of equation, but it's close enough.
Yeah, close.
And yeah, it just happened to have the same initial values, but you can see they get closer and closer to a different.
It's just like recurrence relation, just like in general maths. You just do it over and over again.
Yeah, it's recursive, iterative. Well, I guess no, those are two different words. This would be considered iterative, not recursive. Recursive is a little bit different. Have you done anything programming, computer related?
No, not
Okay.
actually.
Yeah, I'll spare the details of the difference then.
Yeah.
Granted, you do need to know how to write this in pseudocode eventually.
Mm-hmm.
Have you done anything with pseudocode yet?
No, actually, I haven't heard of it yet.
Haven't
First
heard of
time
it yet.
hearing it, but
Okay.
yeah.
That will require a full lesson. And so if you haven't seen anything like this before, it's probably not a good idea to get into that right now. We
Okay.
do only have 15 minutes till end of
Yeah,
class. So.
I'll stay away from that.
Yeah. Yes. And if you're curious at all, I can drop the. I mean, the pseudocode stuff is in the classroom. You can see in the community group. So
Yeah.
maybe check that out if you are interested in having a look at it.
Okay.
But this does sound like it's a bit further from where you're at because you're doing chapter 3 stuff. This is chapter 6 stuff. Yeah, and there's just a few questions on how you might do this here. So one thing they did was say get your answer to a particular number of decimal places.
Mm-hmm.
So under these circumstances, you know for certain it's going to be CAS. In fact, a lot of this will be CAS. Like if you're seeing here, right, like you're not doing any of this by hand. This is a bit crazy.
Oh, so it's all by CAS.
Yeah, like imagine trying to sub in negative 1.125 as your x into this cubic. Like, not fun.
Yeah.
So
definitely.
all this is CAS. You can see they've got these big tables. They're not showing you they're working. It's just CAS. Yeah, that's about it then. So I guess we can see how one of these would look. So we have, in fact, did I just steal this from here? No, this is different, 1 to 2. Okay, so how you might do it on the CAS. The good thing about the CAS is that you can just immediately figure out what your actual answer is, so you can get an idea of if your bisection method even works to begin with.
Okay.
So one thing you might want to do, because you'll be using it a lot, is define your function.
Mm-hmm.
So define x cubed minus x minus 1. Do you know how to do that on the CAS?
No.
Do you have this CAS or the other one?
I have the white CAS here.
Scam. You should buy the new one. We should buy the other one instead. It's significantly better.
Is it the new version?
My one isn't the new version, but I can link you the new version of the TI Inspire. It is better. I can tell you why, but I can. There's a few things.
Well, yeah. Well, I got recommended from my school to get the white CAS instead of.
It was recommended the Casio.
It was actually for, but it is for general maths. It wasn't for methods.
This one that I've got here.
That one.
Is this the one you're talking about?
That one. Yeah.
Disgusting. They must have like a sponsorship or something. It is not,
Maybe.
It is not a great CAS, I'll put it that way.
But
there are some functions. Yeah.
Yeah.
Like one thing that comes to mind is this one cannot complete the square.
You can't?
No, just can't do it. TI Inspire, the black one can.
Wait,
that's just one example.
What's the thing? The model? I will get it.
Oh, you will get it? Oh, I can send you a link to that after class then, and you can just buy it from there.
Okay.
That's fine. But yeah, there's like just some functionalities that you just sort of want to have. But okay, so how to define on. Well, if you're not going to use this, I might as well. I can show you both. Screw it.
Okay.
So if you do end up keeping this because your school forces you to use it, then one thing you might want to do is hit the keyboard button here, and you'll notice now it's one of these, Math 1, 2, or 3.
Math 2, Math 1.
It's one that says define somewhere. Math 3, it looks like. Define.
Math 3?
Yeah. So if you hit the Math 3, hit define.
Oh, yeah.
And then just label your function whatever you want to call it. So you might want to go to the ABC option and say f bracket x is equal to whatever the function is. So in this case, it's x cubed, so x power of 3 This is another reason why I'm not a fan of this one, because it doesn't put things in the power spot. So you typically want to use brackets to make sure. X cubed minus x, and then minus 1. And then just like that, you've got it defined. So now if you were to do, say, f of 3, that's all you have to say to get, like, to say that thing again.
Oh, okay, because 3. For me, it says incorrect number of arguments. I don't know what I put in.
Okay. Did you define it properly? Did it say done here?
No. Mine is just, define f of x, x to the power of 3 minus x minus 1. That's all I have.
Put an equals in there.
Equal.
So click on this spot here with the stylus, put the equal sign in there, and then re-hit enter.
Oh, okay. So after, writing define, and then you got to put equal sign, right?
So it's define, function name, I'll call it f of x, and then equals what the function is.
Yeah. Oh.
That way?
Let me just try that. Oh, yeah, it is. So
Nice.
it's done.
Cool. And now, yeah, if you then type in f bracket anything, it'll give you whatever the y value should be for that thing.
Oh, okay.
So that's how you do it on the Casio, if you are to keep the Casio. For TI Inspire, and you can watch this back on the recording, so you can have that, or just read my CAS document that's also in the classroom. Both are fine. It's found under the menu button. 1 for actions, 1 for define. Then it's the exact same syntax as before. You call it whatever you want, equals whatever it is. X cubed minus x minus 1 in this case. Hit enter, and you get done. If I press the same value, h of 3 in this case, I get 23, which is what it was before. Okay, so that's how you use the CAS. Next bit will be, how do you now do the bisection method? So, bisection method, if you recall, we need to know what our initial upper and lower bound is.
Yeah.
In the question, it says upper bound is 1, and lower bound is 1 and upper bound is 2. The first step of the process is to get the midpoint of those two spots. So the midpoint is just going to be 2 plus 1 all divided by 3. No, all divided by 2, sorry, what am I saying? All divided by 2. And then you test the y value at that spot. So you would do h of. Now, one thing you can do with the CAS is, instead of having to rewrite everything you've just found, you can click this up arrow here, and then either click into it and highlight what you want to copy, or just hit enter on the thing and it'll grab the whole thing.
Okay.
So you can do that, or you can do Control C on it and then Control V. Again, this will be in the recording for you to look at later. In this case, we get a positive number. So 1.5 now becomes our new, what, upper or lower?
1.5? Upper.
Upper, yeah.
Since it is positive, it will be upper, right?
Yeah, exactly. 1.5 is upper. Again, new midpoint. So now we're doing between 1.5 and 1. All divided by 2. 1.25. H of 1.25. Now it's negative. So what do you do
So
from
it'll be
there?
lower.
Lower. Yeah. 1.25 plus 1.5 all divided by 2. And then test the y value at that spot. Positive. Where do we go from here?
Was a positive 1.375?
Yes, the midpoint was 1.375. And then when you test the y value there, you get 0.22.
And you just do it again, don't you?
Yep. So what does 1.375 become? Upper or lower?
Upper.
Upper, yeah. And so yeah, you'll just keep doing this over and over again. 75 plus, it was 1.25 before, all divided by 2, h of, click buttons properly this time.
Mm-hmm.
H of that becomes negative, but it's pretty close. What have we got? 2 decimal places. We want to... Wait, hang on. We actually want to stop. The interval given and the desired accuracy is required. You want x to 2 decimal places. Okay, so you want to keep going until the x value you're subbing in is barely changing anymore.
Okay.
So again, that means now I'm losing track of it. Hang on, 1.25, 1.375. That means whatever this is our new lower. Okay, that plus 1.375 divided by 2, h of that, upper, so 1.34 is new upper, 1.31, 25. So we're getting close now. Now only the second decimal place is changing. You want to keep going until only the third decimal place and above stop changing.
Mm-hmm.
It's that, h of that, 15. Oh, hang on.
That takes a long time in the test, right?
Oh yeah, for sure. This takes, I mean, this particular breakpoint takes a while. Like 2 decimal places for this, not fun. More typically, you'll get something that I showed here. I think this one took, when we were talking about it, maybe 4 or 5. In fact, it was 4 iterations.
Yeah.
Typically, they'll just say do it for 3 iterations.
Okay. Oh.
Yeah, so it doesn't really take like this long. Granted, I have spent a fair bit of time explaining it, but yeah, it doesn't usually take this long. Okay, that's that. Where am I up to? Subbing it in. H of that. Okay, so that's positive, means this is new upper, which means the 1.3125. 31, we're getting close. Copy off that. H of, well, probably should have control entered that. And, okay, should have divided by 2 as well. Very easy to make some mistakes here, unfortunately, because, well, we're throwing a lot of numbers around.
Yeah.
Okay, there's that. Negative 1.32, 1.32. I think we won.
We did?
Yeah, because this is a... No, it's not, because this is the... That was lower. That was upper. 1.32, 1.32. We won. Yeah. 1.32.
1.32 final answer, right?
Yeah, that will be the final answer. So if you were to sub in x equals 1.32, you're close enough to 0.
Negative, yeah.
Which you can see that here, right? Negative 0.01.
Yeah.
Like if we just kill it up a little bit, it's super close. If we actually solve for where it's equal to 0, h of x is equal to 0, comma x. Oh, I shouldn't have hit enter, I should have hit control enter. Now it's going to freeze. Damn it. This is what I was talking about there. Yes, so see how it's sort of freezing.
That's one thing.
Go ahead.
That's one bad thing about, the Teams file. That's why I was cool commanded the cast,
Oh.
They knew.
You reckon it's going to be faster? Okay. I mean, this is an old model. This is a new model. Let's see how much faster this one is. Okay. Because the new TI Inspire should be the same. I mean, you can even check the specs, but having the functionality is definitely better than having a slightly faster CAS, in my opinion. Yeah. Okay, so how would this work? This would be going backwards. You would go to solve. It's a bit hard to see when my camera's in the way. Solve. I call this one f. Solve f of x is equal to 0, comma x bracket. And then shift enter. Oh, wait, no, that's bad. I hit enter and it's still freezing up. So, ha. Granted, it was a bit faster. Still got there a little bit.
Yeah.
But it's just you would hit this button here if you're sticking with this one. 1.32 you can see is approximately the answer, and 1.32 approximately the answer.
Oh,
So yeah, that's how bisection method works. Hopefully that makes sense and you maintain that
yeah.
knowledge by the time you actually get to it.
Chapter 6, right?
Yeah, all the way at the end of chapter 6.
Long way to go.
Not too much longer. Chapter 6 is immediately after chapter 3 in most schools, oddly enough. Just
Oh, it
because,
is?
quadratics are polynomials, and so it makes sense to go to the polynomials chapter immediately after.
Oh, damn.
It might be chapters 4 and 5 though. Some schools do it. It's just most tend to do 6 from what I've seen.
Okay.
Okay, that is end of class. So what I can do is
Mm,
give you the link to that TI Inspire if you're still willing to purchase that because of the new
yep.
the functions. And I guess one thing I want to know is how you thought your first class was. It's kind of a one-on-one rather than a group, but
Yeah, it was one-on-one, to be honest.
yeah.
It was actually really good, we did go through the questions that we had and then,
Yeah,
extra
precisely.
lesson on that. Yeah,
So
be amazing.
yeah, so one-on-ones would be more of what we did at the beginning, which was doing your specific questions and drilling those, and then I get to
Mhm.
pick what you're specifically having issues with. Whereas the groups, after I go through the groups classes, the questions, if we get to this stage, we then do the curriculum content,
Oh,
which,
okay.
as you've seen, just going through the questions already, may take us to the end of the class anyway.
Yeah,
So
definitely.
that's the main differences between the groups and the privates.